It's a real pleasure to introduce Gerald Bawden as our Bowie lecturer for 2010. Gerald received his PhD in 1998 from University of California at Davis. Currently, he's the chief scientist at the USGS Western Remote Sensing and Visualization Center in Sacramento and a staff scientist for the USGS Pacific Southwest Regional Executive Office. In addition, he's an adjunct professor at Cal State University Sacramento and a research associate at UC Davis in their geology department. As we'll see, his research is focused on mechanisms that drive natural and human-induced disasters. He uses satellite, airborne, and ground-based surveying techniques to measure changes in the Earth's surface associated with land subsidence, earthquakes, and volcanic activity. I first became aware of Gerald's work when we and a number of other groups were looking at radar interferometry in the Los Angeles basin, trying to understand it in terms of tectonics. And we were baffled because we had faults moving in the wrong direction and they were moving too fast. And Gerald and his colleagues came up with the right answer. It had nothing to do with tectonics. It was groundwater causing the LA basin to move up and down by 5 centimeters or so. Since then, Gerald has used a number of geodetic tools of radar, LiDAR to explore a wide variety of human and natural processes, and I think we'll hear about some of these, of course. In order to display his 4D data, Gerald proposes to do this lecture in 3D, of course, and I think this is the first use of 3D at an AGU, probably for such a large audience. I remember back in the Magellan days we did things in 3D, but I haven't seen this for quite a while. So the title of his presentation is Ultra High Resolution 4-Dimensional Imaging Across the Earth Sciences.
Thank you so much, David. Hopefully everybody's had a chance to pick up a pair of 3D glasses in the back. There'll be a number of animations throughout the presentation where we take advantage of the 3D technology. You're also going to have to bear with me a little bit with regard to my talk. It's over 10 gigabytes in size. I've crashed my computer numerous times with it, just trying to get the talk together. So what I've had to do is break it into some smaller segments such that the computer could handle the speed. We're in an exciting time right now in geodesy. Over the past 10 years or 20 years, there have been some significant advances in geodesy. With the advent of GPS, we came to a point where historically we've been surveying across fault zones with apertures about 10, 20 kilometers across, doing traditional surveying with trilateration triangulation. And then GPS came along. It allowed us to go ahead and very precisely measure benchmarks. Instead of looking at deformation in close, we're now looking at full deforming plate boundaries. The EarthScope project, Plate Boundary Observatory, is an example of where we've got about 1,000 continuous GPS receivers running from Mexico up to the Canadian border and Alaska. New networks going in the Caribbean and elsewhere. GPS has completely revolutionized how we look at the Earth, how it's moving, and also it's given us new reference frames. Synthetic aperture radar interferometry, satellite radar. This is a technique where you've got an orbiting radar satellite. It takes snapshots of the Earth from the same point in space at 2 different times. You're able to precisely align the imagery. And from that, differencing it produces an interferogram, a map of what the deformation is. INSAR has allowed us to now start looking at spatially varying deformation. GPS, you've got the point position. Now, with the advent of LiDAR, the first go around with it is basically airborne, where you basically have an aircraft, GPS, so you know exactly the position of the aircraft. You got a laser scanner on it, it shoots out now up to 100,000 times per second, and you know the travel time, speed of light, and you're able to go ahead and uniquely calculate the coordinates of that laser spot on the ground. LiDAR has brought about a number of incredible discoveries. It's allowed us to go ahead and look at the Earth through new glasses. It's 3-dimensional data. GPS is a point. INSAR is 2D data with a little bit of range change. LiDAR is the first true 3-dimensional data that we have. One of the wonderful things you're able to do with it for airborne is to go ahead and strip off vegetation. So by stripping off the vegetation, you're now able to look through the trees at the ground surface. Ralph Halygaard and others up in Washington have found new faults right close to Seattle, all based on the ability to go ahead and strip off the trees. I'm working on a project up near Lake Tahoe, where it's an area where there has been mapping for over 100 years, and we found a brand new, new fault. We're able to put the pieces together. It's capable of approximately a magnitude 7 earthquake. It was the LiDAR that was able to shed light on it. So, as scientists, we like building bigger telescopes, bigger instruments to go ahead and be able to view farther into space, deeper in space, seeing smaller things, going back further in time. And at some point, we need to turn that telescope inward and look closer in at some of the small processes that make up the overall. And that's where ground-based LiDAR is. We're not going to be imaging the whole San Andreas Fault with 1 centimeter spot spacing. But we can image pieces of the San Andreas Fault and other areas to understand some of the small-scale processes that then drive into the overall picture. So I'm going to give some examples this afternoon in 4 different areas, 4 different applications for ground-based LiDAR. With those, we'll look at debris flows in Southern California, spatially varying snow depth in the Sierras as it relates to climate change. We're going to look at levee stability and the effects that growing trees have on levees. But I want to first start off with the Parkfield earthquake. Before I really dive into it, I do have a few key acknowledgments that I'd like to go ahead and acknowledge. With any group, it takes a number of people to make things work out. Jim Hell is my field guy extraordinaire, mountain goat. Sandra Bond is able to sit down for weeks on end processing data to be able to get as much as we can out of that. We're still in evolving technology. We've got a number of years before the technology is mature, and Sandra's been leading the forefront with the processing. Mike Schulters, and we actually have some names at the bottom, so we're missing the bottom couple inches on the slide. We've got Bonnie Thompson and Robert Mason from the USGS, along with Mike Schulters. They saw my vision. They helped fund, and they've given me the time and funding to go ahead and make this work. Louise Kellogg and Oliver Kryalos with the UC Davis Keck Caves. You notice on the logos we have the Keck Caves. They've got Louise had an idea of trying to blend computer science with earth science. And they've got a 3D virtual reality room, of which I've been blessed with being a part of the university and being able to take advantage of it. The 3D animations that we're going to see here were all developed due to Oliver's work and Louise's vision. So let's start with getting into some of the science. First with the tectonics. With ground-based LiDAR, there's a number of different applications, uses that we do with LiDAR for tectonics. One talked about the Polaris Fault. This is one of the laser scanners I have. This is a newly developed elevated tripod. Did not exist before. I was able to find a company in Canada. We've got it developed, and now a number of universities and other institutions are now using it. But in scanning the Polaris Fault, we're able to fit surfaces to the plane up here, the slope here, come up with piercing points and determine what the slip history is. We're able to make ultra-high resolution digital elevation models. This is a 3 centimeter digital elevation model. They're able to go through and do very detailed geomorphology with it. We worked with Ken Hunnett and David Phillips looking at precariously balancing rocks, looking at creep along the northern San Andreas Fault, looking at offsets of structures. This is the UC Berkeley Stadium that is slowly, and the Hayward Fault goes through. We're able to look at the offset there. But most of the time what I want to do is start talking about Parkfield. Why Parkfield? Well, I took delivery of my first ground-based LiDAR instrument on Monday. My first scan was in my office. Went home that night. Next morning, we had the Parkfield earthquake. I did my roles and responsibilities as the chair of the PBO site selection committee. We figured out where to put the GPS. And then I got up early and went down and did some scans in Parkfield. My first scan was the bridge and a number of other places. Came back, and we started piecing together a pretty intriguing story that you're going to learn. So what I'd like to do is, this is us, this is Moscone. We're approximately right here. We're going to go ahead and fly down to Parkfield. The red line on the right, it will be the San Andreas Fault. These are basically showing the historic San Andreas coming up through here, and we have some of the Hayward off there. The Parkfield earthquake, it's an area in California that is well known within the geodesy, and actually in the geology community in general. Approximately every 22 years, there's about a magnitude 6 earthquake that takes place in Parkfield, which is a small little dot out here. I think with population 22. Since they figured that we had this regular earthquake every 22 years, it would be actually an ideal time to go ahead and test a number of different instruments. What can we learn about the geophysics of the Earth? How did the Earth fail? Also, you have engineering structure and stuff that went in. So it's an incredible playground. It's arguably the most densely instrumented fault section in the world. And here I come down the day after the earthquake with some new technology and find some new discoveries. So we're going to spend time looking at 2 different areas. This is the Parkfield Bridge. The San Andreas comes through here. I've got a sag pond up over Collar Hill through this direction here. Here's an aerial photo taken by Ramon Aerosmith. We got the right lateral motion through here, and here's the dates of the past earthquakes. With the map here, what we were anticipating with the Parkfield earthquake was that it would happen in the same spot to the north that it had regularly taken place. And indeed, what happened is it actually took place south of Parkfield. So it was, again, unexpected. But here's the location of the earthquake. Zoom in, there's Parkfield Bridge, that's the first spot. And there's a small building there that we'll be able to see. So how does ground-based LiDAR work? Our first job is to go ahead and set up the instrument. It's a laser scanner, and just like with the airborne, it shoots out a laser. So imagine we've got the laser coming back and forth right here. It's able to go ahead and scan up and create an image. It's also very much like the floodlights that are blinding me right now. All the energy, all the photons are coming in one direction. It can't see the behind me. And so what I've got to do is relocate the instrument off to the side to fill in fill in shadows behind me. So this is the idea behind the LiDAR. So here's what it looks like from a laser scan. So this is an actual laser scan. I've got 4 millimeter spot spacing out at 20 meters. And you can see the Parkfield Bridge. There's actually a kink in the bridge as it's slowly deforming with the San Andreas Fault running under it. This is the March 2005 survey. Each of the stars is a location that we set up to try to minimize shadowing within it. The 2 stars here are the spots that we surveyed every single time. Again, going back, this was effectively my second scan. I'm still going through the learning curve on how to run surveys, but we've still got a lot of data from it. So you set up, you align it. What we did, these are fault fracture maps, courtesy of Ramon Aerosmith, and so he mapped the fractures coming up. And right under the bridge, there's a bifurcation displaying the fault, and we're going to actually see deformation associated with that junction there. So once we have the data aligned, what I have to do here is to align the data on the San Andreas Fault. These blue lines here are the map traces that Ramon had, and we bring in the map trace. So now that's the y-axis. It's looking straight up. So now it's going to be very easy for me to look at fault parallel motion as well as fault perpendicular motion. So now let's go ahead and put the 3D glasses on, and I want to show you what the actual alignment looks like. You're going to see that this is 3D data. I could look at things upside down, inside out, however you'd like. So we're going to actually start off by heading under the ground. We're underground. We're looking at the support structures right through here. This is the deck of the bridge up here. You can see the bend. Here's the guardrail. It comes across midway. It is deflected off to the right. As we have right, this is the San Andreas Fault. In fact, it comes in between these 2 support structures. You can look down these support structures. We'll notice that elsewhere, they come in a very nice line, and then they start getting close to the fault. You actually see them offset by a fair amount. So what we're recording here is the bridge went in a while ago. Unfortunately, I forget what the date is. So you can see the nice line here. This one's offset, and so on there. This was built as a straight bridge. So all the kinks that we're seeing in it is what the creeping part of the San Andreas Fault is doing. This part of the San Andreas creeps about 1.3 centimeters a year. So it's just slowly moving along. We have the Parkfield earthquake. It moves fast, or it moves an inch or 2, and then it slowly recovers back down to the 1 1/3. We're now going under the ground, and we're looking up at the guardrail post. And the reason I'm doing this is we're going to spend a little bit of time looking at this structure right here. This is one of the support structures. You can see the cylinder here, and then there's the structure around it. Again, this is three-dimensional data. Unlike the other geodetic techniques, especially with GPS where you need to see the sky, this, you're able to go ahead, scan caves, you can scan anything, and work with it in any orientation that's needed. We're going to fly up through here, take a look at some of these signposts. You'll see some lines right over on these sides here, and I'll point out on the other screen over here. Those are cars driving by. So as they drive by, there are actually some lines down below next to the structures. That's when I basically got a scan started and ran down and did some measuring underneath the bridge. This is one of the signposts that says Parkfield and I think Vineyard Canyon Road. So this is just one of the standard street signs. Here's another street sign here. You're going to see later on in the talk, I'm actually using these as geodetic benchmarks to track the deformation, track the earthquake, how the post-seismic worked. I'm coming up with more data points, tighter in than one would expect in putting in any other geodetic network. So as this animation starts winding up, the next slide that I'm going to show you is going to be a difference. So my first survey was the day after the Parkfield earthquake. I came back exactly 10 weeks later and rescanned. What I did is I aligned this part of the bridge, this structure here, and the deck of the bridge, and allowed everything else to float. And so if there was no motion, this side of the bridge, these structures over here would perfectly, uniquely line up. If there was motion, then we'd actually see an offset. So the color plot, you're going to see areas that are green did not change much. Areas that are in red and blue have changed. Now, one warning with this next slide, if you got your 3D glasses on, it might hurt. So here we are. We're standing on, or just above the North American plate, looking across at the Pacific plate. See the support structures here, solid green, solid green. All of a sudden we get out here, which is about 7 centimeters worth of displacement. Now you can see these signposts out here, all moving along. The next plot that I want to show you, same concept, but I'm going to go now from September in through July, so a 43-week period. And due to computer crashing issues, I ended up chopping out the trees just so we could focus on the bridge. And as we come across here, we see very nicely what's going that basically, as soon as we get close to where Ramon Aerosmith's mapping the fault, we actually see a fair amount of motion. At this point here, we're dealing with close to 12 centimeters worth of displacement. Now what I want to do is take a look looking straight down at the cylinder structure. One nice thing with the 3D data, so this is looking down, here's the edge of the structure, and then there's a cylinder. I'll point it out on the other side as well. With Excel, you're able to go ahead and best fit lines through scatters of data. With 3D data, I could best fit primitives, mathematical structures, to the data. And from that, I'm able to go ahead and fit, this is a cylinder. Caltrans uses feet, so it's a 2-foot diameter structure. I fit a best fit cylinder to it. The center of the cylinder is a vector. So here's the cylinder. The center of a cylinder is a vector where a vector meets a plane, and this plane is basically the deck of the bridge, fit a best fit plane to it, lowered it down to the center of the cylinder. That's a unique point. And then I'm able to track its position with time. So from September, December, with the vectors, found out that the center of the bridge moved 7.1 centimeters. We could take it the next step, going from September to March, another 2.6 centimeters worth of deformation, with a grand total of 9.1. So what's going on with the bridge at this point? We're seeing that the bottom is moving a fair amount. And if we take a look at, this is the same color plot that we looked at before, we see that the deck of the bridge, it's moving a bit. It's in green, but it's actually kind of up at it should be right about 0.3 or 3 centimeters. And down here, at this point here, we've got over 12, actually about 12 centimeters worth of motion. Now, what we look at, these blue lines here, that's not tectonic. Those are geologists, footprints heading down to take a look at the bridge. So every time they step down, they actually are patting it down. You can see a lot of blue around here patting down the grass. So what's going on in here? We've got the green, we've got the red. So there's obviously something going on at the bridge. Is it safe to drive across the bridge? Don't know. The other thing that I actually really want to point out is there's a little structure in through here. This is where the faults actually come together. You got the splay through here. It's a relatively small feature, about 3-4 meters across in total length. Did some preliminary modeling on it, because basically we got 2 different fault strands. Which one is active during this time period? And to have upwards of 5 centimeters of subsidence, you actually needed to have the rightmost strand as the primary active strand. That way you have a small pull apart, it's dropping down. The wavelength of this would not be seen with any other geodetic technique unless you had benchmarks every quarter meter heading across, or even tighter. So now, getting back to the bridge, what's going on? This is a very detailed 1 millimeter scan of this area here. Why did I scan it? Well, I wanted to really start tracking this. The deck of the bridge is sitting on rubber. These are rubber pads. Right here, you can see where they're slowly folding under as it's moving along, effectively leaving a skid mark. And here's that very skid mark. You can see where the deck of the bridge was up to the day of the earthquake. It left this really nice shadow here, and then it slid off. So with it, we're able to measure it, and 11.4 centimeters is what I found deforming of the bridge. If you remember, a minute ago I said the tripod LiDAR came up with 9.1. So what's the difference? The difference is again, I got my scanner on Monday. If I had the vision to head down to Parkfield that instant, I could have gotten the coseismic. But instead, by measuring the difference between the skid mark and the ground-based is basically the coseismic, which is 2.3 centimeters, plus the first day of afterslip. Caltrans has a report out there that says that the bridge moved by 1 centimeter, by 1 inch, basically 25 millimeters. Now, they're not factoring in the fact that the bottom of the bridge actually deformed. It bent upwards of 3 centimeters. So the coseismic slip of the bridge in reality is about double this. So let's go ahead and put on 3D glasses again. And now what I want to do is fly through the LiDAR data. This time we've got 3 different colors. We have white, which is the initial one, the day after the earthquake, yellow, which is the 10 weeks, and the blue is the 3 week, in March. And this is the area that I held fixed. And so what I'm hoping to show here is that with the alignment in 3D, you're able to see that on either side of the structure, you basically have all the colors perfectly commingled. That means I've got a good alignment. If I see some sort of bias where I've got one color on one side and not on the other side, then it's either poor alignment or we've had some sort of deformation. Now, the other spot that I held fixed was the deck of the bridge. And so what I want to do is basically fly over to the bridge, and I'm going to do an Alice in Wonderland thing. We're going to get really, really, really small now. This scatter here is plus or minus 8 millimeters, and I'm going to have it up on here, which is going to be on the order of about 1 meter tall. You can see we have a very tight alignment here. There's perfectly uniform distribution of the data throughout here. So we've got our reference frame, and this is the reason I'm emphasizing so much. These 2 structures are a reference frame. If we've got a poor alignment there, then we're going to miss it. Now we're flying along the I-beam as we head out to the center of the bridge. This deflection here, again, this I-beam used to be straight all the way across. This deflection is the bridge deforming. Back there, we had very nice agreement with the data. Now what we're starting to see is on the left side, which on both sides over here, we're starting to see the yellow and the white data come out on the left side. That is the coseismic and the post-seismic deformation of the I-beam. Now I want to take a look, looking straight down at the structure. And again, like what we saw with the primitives, you can see the offset rings of the central piers. So the white is our original one, yellow is the 10 weeks, and then 23 weeks with the blue. You can also see the side of the support structure also deforming. We're going to fly up a little bit higher and then come down and look at the last support structure before working way up a little bit further. Some of this in here is basically vegetation that grew in the March data set, which we had to go through and ultimately delete if we needed to do any calculations in here. So you can see the offsets through here. As a technique, we're now able to start using all sorts of geomorphic and structural features to look at displacements. By fitting mathematical primitives, by fitting meshes to the data, we're able to go ahead and extract out displacements. We just passed by some fence posts. We're going to come to that street sign that we saw. There's the cross. So all we've got to do is fit a best fit vector to the street sign. or the intersection of two planes is a vector. Where it intersects a plane is a point. We're able to go ahead and extract out these as deforming points, unique points. I'm now able to use chain link fences, signs, and everything. This is Jim Linkamper doing a trilateration survey across the bridge the day after the earthquake. So we basically have both new school and old school working together here. The Parkfield earthquake was not the only thing that caused deformation in the Parkfield area. We're now flying down through the bridge, and there was a major flood that took place in March. So this is the land surface from both September and December, and we're seeing upwards of 1.25 meters worth of erosion. We got bridge scour and everything going on here. So that's looking at the bridge. Now what I'd like to do is go up and take a look at Carr Hill. This is where the USGS installed a video camera array. Oh yeah, please take off your glasses, sorry. The USGS installed a video camera array. People have talked about, there's eyewitness accounts of standing and watching earthquake waves come. And so the question is, what is it? It doesn't make sense scientifically, but let's go ahead and put up some video cameras, have them turn on when you have a magnitude 4.5 or larger earthquake, and record the motion. And so we've got a video camera over my right shoulder, and we're going to take a look at the Parkfield earthquake. So this is the video camera turning on. The white cylinders were put in basically as references. So your eye had something to track during the earthquake so you could see some motion going on. So that was the Parkfield earthquake. This video camera array has served incredible for studying deformation following the earthquake. This is the ground base LiDAR survey. You can basically see these, the cross coming up here. Here's the second video camera looking this way. So the next plot I'm going to show you is one of these difference plots. This time I'm holding the Pacific plate fixed. So on the left, that's held fixed, and I'm allowing the North American plate to move along. And the colors that are in green did not move much. Colors that are in blue have upwards of 8 centimeters worth of displacement. And the little bit of red in here was a bit of vegetation change. You can see a very pronounced blue line coming right through here. That's the fault. At Carr Hill, the San Andreas Fault is confined to a very narrow region, probably about 1.5 meters wide. I'm now looking at changes in the geomorphology. This is a cow field out there. There's a lot of cow pies. I'm actually tracking cow pies as deformation. We also have other instrumentation in the area. John Langbein runs a creep meter that goes across the fault, and here's where the data is telemetry. So this is satellite telemetry. This is the ground base LiDAR. And what I do is I best fit planes to the side of either side of this. The intersection of two planes is a vector. Where it intersects the ground is a point. We can do the same thing with the cylinder structure here. Now I'm just grabbing all these new points, and I'm able to work on understanding the deformation with it. So now what I'd like to do is go back to here, and we're going to now look across and perpendicular to the San Andreas Fault, where I did primitive modeling of the cylinders. And again, the far side, the Pacific plate is held fixed. You can see no motion coming down through here. Believe it or not, there are both red and yellow cylinders on all these. But as soon as we get right here, we see upwards of 2.2 centimeters worth of motion, and you work your way up to over 7 centimeters worth of motion, all within this. We did an elevation difference as well. So this is looking at some of the vectors going through here. And I've got something that I've actually not been able to explain yet, and maybe someone after the talk we can try to put our heads together with it. In the 10 weeks after the Parkfield earthquake, I see upwards of 5 centimeters worth of uplift within the fault zone. You're going to see elsewhere where we actually see extensions. We have uplift and extension that's going on, and then later on we develop a bunch of pits that drop down. Some of these pits are upwards of 2/3 of a meter deep. So pits are generally from an extensional regime. Uplift is from a compressional regime. How can you get both things going on in the very narrow fault zone? We also found there was both fault parallel motion as well as fault perpendicular motion. If you look at the cylinders coming across, you can actually see the yellow one out a little bit more. So there's an incredible story that we're trying to ultimately sort out from here. Omori's law is a way of basically trying, it looks at how the expected slip rate decay following an earthquake is. And you got rate inversely proportional with time. And John Langmane's got the two creep meters that run across the San Andreas Fault right at Carr Hill. In fact, we've got some of the data coming out from it. And the black line represents the typical decay that we'd expect to have, and the blue line represents the data. XTA is a deeper creep meter. TBC is basically a shallower one. And you can actually see there's actually some deviations within this. And the ground-based LiDAR ultimately sees the same thing. So we're now Pacific Plate here, North American Plate here. The side over here is held fixed. Areas that are green, these are tree trunks, these are the cylinders, these are fence posts. And this is the creep meter. The creep meter, it's a wire that's strung across the fault, and as the fault moves, it pulls on the string, it gets longer, and you're able to measure it. But it's only measuring effectively one-dimensional deformation. So if you separate it out to the fault perpendicular or fault parallel, this is what the length of the vectors would be. And so as we come across the San Andreas Fault, this is where I was talking about having extension. Then we have fault normal extension, as well as a fairly strong 9-centimeter right lateral strike slip. And then when we hit up here, just out of the fault zone, a lot more fault parallel. Now we take, so at the bottom, we're supposed to be saying this is 2004, so this is timelines along here. For the next time period, within this is the area where I basically said that we had the 5 centimeters worth of uplift. You can see the edge of the boundary there and here. It all makes sense with the vectors. We've got deformation. What's causing it? We take the next time period, so this is December and through March. We now have very strong fault normal contraction with these vectors heading in this way, and there's also what appears to be a little bit of reverse motion within the fault zone itself. We move onward from in through June, so now we're looking at March to June. We still got continued right lateral strike slip. So if we add it up for the full 41 weeks, we have almost pure right lateral strike slip, upwards of 16 centimeters worth of slip. It's almost all perfectly heading off this way. And the length of the strain meter definitely matches in with the creep meter. So one thing that's validating what I'm seeing with the ground-based LiDAR, and that we could also use trees, fence posts, and come up with deformation patterns that are very consistent with very precise, high-resolution creep meter data, which I find it's mind-boggling. And this is the area where the 5 centimeter uplift took place. I only saw it in the first time period. It did not persist later on. So if I could take it back and tie it in with Omori's law. This is looking at Omori's law and then subtracting off what we see at the creep meter. So this is the residual. This is the unexplained. So this is Omori's law heading through here, so we have the time. On the bottom, this is rain, because it's often figured that a lot of shallow earth processes are driven by rain. The first rainfall started well after, took place well after the beginning of the deviation for Omori's law. So the fault normal extension, we can basically be explained by this going up to here. So with the ground-based LiDAR, we have this measurement here. It heads up here. So we're seeing, again, the fault expand and then drop down. The Omori's law was using the creep meter. The deviations with the creep meter only looks one direction. We're looking at two directions, so we're actually seeing the expansion and the contraction across the fault zone. So now we're going to leave the Parkfield earthquake. We're going to fly up the San Andreas, and we're going to deviate into Sacramento and start looking at levee stability questions. The Corps of Engineers they are looking at the role that trees play on levees. They've got 2-year research before they're going to actually start potentially initiating a program of chopping down all trees across the United States on levees within 15 feet. And so the question is, what do trees do on levees? Do they stabilize the soil, or do they act as conduits for water migration through it, or wind knockdown events, so forth? This is the Jones Tract levee failure, which took place about 100 kilometers due east of here in 2005. California, in this area here, we have over 1,000 miles worth of levees. The Corps of Engineers issue is roots can penetrate levees. So this is a shot from the Corps of Engineers up in Oregon, and here's roots running all the way through a levee, and it was basically contributed to acknowledging the failure of this particular levee. There are a couple possible sources. The Corps of Engineers believes that with the trees, you got the roots growing into the levees, and it could act as conduits for water seeping through. I've got a number of projects working with levee stability, with using INSAR, UAV SAR, and now with ground-based LiDAR. The image on the right here, this is an animation. This is a slurry wall. It's where they've gone back, dug a deep trench across a levee, and dumped in basically a bentonite concrete combination. So you're creating a quasi-rigid wall. And what was really curious that we found is that there are roots that can penetrate this. And some of them go in and then follow along into the bentonite, into the slurry wall, something that was completely unexpected. The ground-based LiDAR is providing the whole three-dimensional reference frame for this. We also are looking at how water flows through stumps. So here's a stump that died or a tree that died in 1995, dug a trench upside, downside, filled the upper side with water, and measured how quick the water flowed across it. From the ground-based LiDAR side, we ended up doing is slowly excavating the trunk and creating a true three-dimensional representation of this levee stump. And that's going to be folded in with the modeling. You can actually put your glasses on for this one. This is our two trees that we're going to get to know a little bit more intimately coming up. The blue and the red are oak trees. These are common valley oak. And the yellow one is a cottonwood. And you can see we've got different species, and the tree roots are doing significantly different things. So what I did, went out, and so this is looking at those two tree roots. Here's the tree on the left, here's the tree on the right, and took a scan beforehand, and then my colleagues at UC Davis developed something called an air knife. It's basically compressed air, and they slowly and painstakingly blew out all of the soil around the levees, around the tree roots, and I was able to come in and then do three-dimensional imaging. Both with my instrument, and also I borrowed an instrument from UNAVCO, a Leica system, which is really high-resolution scanning. So go ahead and put your glasses back on. We're going to take a three-stage animation through this tree. What I've got here, this is a tree that was actually excavated in a field, not on a levee, although I did put it on a levee, and I think my colleagues would like to shoot me for that, but this is on top of the levee. These are the roots. I'm going to go ahead and fly through and take a look at what this root system looks like. So the tree is falling back, and we're now heading under the levee, and as the roots come across. One of the things that I'd really like to know is look at the even radial distribution of these tree roots. There's no asymmetry with it whatsoever. All the roots are, I'll just say, relatively uniform in size for the larger major roots. And this is the same tree where I basically chopped the top, virtually chopped the top off. And you can see, very nice uniform radial pattern. Now what I'm going to do is I'm going to switch modes. We're going to look at it as more of a surface instead of a point cloud data. And now we're able to look at the surface of the roots. And we're going to fly from here, and we're going to head over and take a look straight down on to the next tree. And I want to try to get a pause in if it lets me. It's not going to let me pause. One of the things we're going to see is there's strong asymmetry. There's a very strong root here. There's also coming out this way. This tree on the steepest part of the levee is actually growing very asymmetric. It's putting out strong roots parallel and then down levee, and it has less up levee. We also found roots that came up and held about 10 centimeters under the levee and continued growing up the levee at a uniform depth. Now I'm going to switch to color. The blue is going to be the tree on the right, and the yellow is the cottonwood. And we're now underground looking in close. We're actually probably, we're much larger than life size here. Some of these roots here, that's probably about 5 centimeters across. The other thing that we found with the trees that grew in the levees is a very strong pseudo-taproot. This was something that was completely unexpected. Most oaks do not have much of a taproot or a structure underneath. The roots tend to head out. And both of these trees had much more dominant taproots than their other cousins did. This tree here is located a little bit further away from the steepest part of the levee. You can see through here. And its roots have more of a typical pattern. There's not this asymmetry with it. They're just growing out and then down with a little bit heading up. And these dark points are little scatter points from the levee top itself. So one of the things that we've done with this is we began vectorizing these roots. Take off your glasses. This is now looking down the roots, and we developed a way of fitting best fit vectors to the center of the roots. And what I've done is the major blue roots are, the major thick blue lines are the major roots, and as they come down, they bifurcate. We've got different coatings within it. As we animate it, we're going to move around. These blue stripes are here are approximately 1/3 of a meter or a foot in size. And so now we're working on providing the engineers and the biologists new three-dimensional data on being able to understand how this grows. There's a long laundry list of things that they're interested in. You got more roots, okay, you got slope, you have solar, whatever side the sun is on, you're going to have a lot more roots. Taper is a function, branching. We now have a unique way to go ahead and 3D characterize the roots and how they're growing. Then this then starts folding into tree root modeling for levee stability. Now I'm going to quickly leave the roots and head up to the southern Sierras, actually northern Sierras. I had a crazy idea one morning. How well would ground-based LiDAR work in the snow? A couple phone calls later, I found myself up on at the Central Sierra Snow Lab up on Donner Summit in actually a pretty major snowstorm. It wasn't supposed to snow, but we got it. It's a snow lab in which we have to go ahead and hike our instruments, our snowshoe, cross-country ski our instruments in. And I'm going to take a quick exit here and get the next one going. Okay. So I've done I've had a growing list of research projects working in the cryosphere and in snow science, working with Ed Josberger, trying to look at and characterize glacial mass balance of the Nisqually Glacier on Mount Rainier. We've tested, we're actually trying to test another instrument. Done work up on Tioga Pass after it's closed. It's an area where they've got avalanches. But I'm going to spend a fair amount of my time here just really discussing snow melt. So off to the Central Sierra Snow Lab. Here's the entrance to it. We did a scan on March 23rd. The first scan, this is a no-weather gauge. You can see these towers and these structures off through here. This is where we've got all sorts of different instrumentation. This is an area where it's a test bed for technology. And then we came back April 29th, rescanned, and then scanned again when basically the snow had melted. With what we did with the Parkfield earthquake, we were able to do difference plots. Now I'm able to do the same thing with the snow, and we found 2 to 3 meters snow depth uniformly across, not uniformly. There's actually a variation in the color palette through here, of which I could talk about the significance later on. But what we do see is, what's nice is we can uniquely measure the 3D volume. And instead of at point sources, which is traditionally how it's done, we could also calculate the volume. If you know what the snow water equivalent is, then you're able to say, what's the cubic volume of water? Water resource managers need this information to know how much water is coming into Hetch Hetchy Reservoir. If we've got a storm coming in, do we let out water or how do we maintain it? This is what we're hoping to do, is be able to take this to a much broader and look at basin scale water quantities. So within this, there's 32.7 cubic meters of water above the lysimeters. And lysimeters, these are boxes on the ground that collect water, and the water comes down to the lower corner on each one, and there's a tipping bucket rain gauge. So it's a snow rain gauge. And we're able to calculate the exact volume of the water. So I differenced the March to April data and found almost a uniform meter worth of snow melt during that time period, with the exception of off to the left on either side where you see dark blue. It's an area where we have a south-facing slope, and we might be getting a little bit more solar radiation in there. So on this time period here, we had 28.4 cubic meters worth of water, or about 7,400 gallons of water. And what we're able to do is calculate how well did the water from the ground-based LiDAR versus the lysimeters add up. The discrepancy is likely due to sublimation, and that's a key part. That's going from snow, crystal ice into vapor, and is completely bypassing the water component. Sublimation is a key component for doing climate modeling, for understanding, being able to translate snow depth to real water availability. So to go ahead and put your 3D glasses on, we're now going to go ahead and do something that you can only do if you fall into a deep snowdrift. We're going to go into the snow. So this is the Central Sierra Snow Lab. You can see the drift snow off the roof. The white is the March, yellow is April, and then the blue is June, where there's still a little bit of snow on the ground. We're heading out to the NOAA gauge out here. Again, this depth here is about 1 meter. And now we're going to go ahead and start walking under the snow. This is probably about life size. 3 meters is about 10 feet. This is a 10-foot tall screen. So we're seeing this real height. So basically, if I was walking across here, my head would be barely popping out of here. Here's a ladder that they use to go ahead and climb up. And I'm not going to be able to pause this. What we're going to see is when we head up to the very top, I've got 2 white data sets that don't necessarily line up right through here. You've got a light data set there and a data set through there. And I kind of scratched my head at first trying to understand why was that. Then I remembered it was snowing. And I had multiple setups because I had to fill in the shadows. I was actually able to measure how much snow had accumulated in that time period. So now what I want to do is jump to another animation. So what I was before is optimizing surfaces. Now I want to optimize looking at things that are in the air. So here's the LiDAR surface. This is the ladder they used to get up, and as they climb up and down and also get more snow load on the ladder, it actually moves around. With the 3D, you might start making out little points up here. With the ground-based LiDAR, I'm able to collect the first return and the last return. The first return is basically when the laser, say if it hits this rail here or hits my hand first, and the second part would be when it's hitting the screen. Almost all the data that I collected was all last return, except for I really wanted to nail my reference frame looking in this direction, so I did first return on these towers, not even considering that I could actually count every single snowflake that was falling. And indeed, that's what we did. So I think we've got, with a little bit of calibration, we can have a technique to go ahead and measure and count the number of snowflakes that are falling within here. Here's satellite telemetry off through here. So new techniques, new capabilities, and we've had a lot of ideas for doing avalanche hazard work with this. So as we leave here, go ahead and take the glasses off. I got one last section. We're going to go down to Southern California and look at debris flows. You've got some of the fastest rising mountains in the world in Southern California. Whoops, actually, I'm getting ahead of myself. We're heading down to take a look at some climate change data. My apologies. This is Conway Summit, which is down just north of Mono Basin. This is where I'm working with Alan and Lori Flint, scientists at the USGS California Water Science Center. And they're the climate modelers. They're taking the snowfall data, and they're used to having information at one point on the ground, a snow bellow, a weather station. And what I'm able to do is start taking this and expanding it into full 3D. We all intuitively know that south-facing slopes will have more snow, or basically south-facing slopes get more solar radiation, so the water is going to melt quicker, or the snow will melt quicker, and in north-facing slopes, or in the shadows, we'll have less. We know that. How do we quantify this? Ground-based LiDAR has allowed us to go through and really be able to start looking and nailing that part, taking that information, folding it into climate models. So here's what the area looks like. We have since gone through, did vegetation removal, so we're now able to get the bare earth surface. Here's one of the scans heading across here and out here. And here's what it looks like just as a digital elevation model, where the green is the snow. You can see wind streaks up here. We got more snow behind some of the brush with some of the wind. Like before, I've been doing a difference plot where blue is very thin snow down to red, which is up to 2 meters worth of snow. So you got a fairly large snow drift here. You got snow up here. Then in March, the snowdrift, or this down here, expanded, then slowly melted away with time, and then finally in May, there was not much left. Now, for climate modeling, we've condensed things down to grid cells. And so these are the grid cells where we had consistent data. And they then took the snow water equivalent for each of these grid cells, put it into their time series, and was able to calculate how much water they had expected in each of the different cells. And the blue is the modeled. The areas here that have S are south-facing. These are south-facing slopes. These are north-facing slopes. And we have the different time periods here. What we found is that we measured a lot more snow than what their model predicted on the north-facing slopes, and there was a lot less snow on the south-facing slopes than what their model predicted. And this could be said for in April as well, and taking it all the way down. But one thing that adding solar radiation into the models really worked with was actually doing the difference. So now we're looking at the difference between March and April, that the new information in their model, you're able to actually see for the north-facing slopes, we actually had a reasonable agreement, and with the south-facing slopes, there's still a little bit of work. But we're in the infancy here with the modeling. So now we're going to head off to Southern California with the debris flows. Southern California, since 2000, has got another season. It's called fire season. And this is actually one of the first years in a while that we've not had a major fire. I've been a part of a team where we're going out and trying to do quantitative geomorphology on a lot of the fires, trying to understand the processes and the mechanisms that lead to debris flows. This is one above, this is the station fire above Pasadena, and Google Earth has a wonderful image of it. And this is almost as good as I could do. Here's a basin that we heavily instrumented. You could see the rilling, so this is post some of the storms that have gone through. And we're going to spend a fair amount of time with that. But I also want to take a quick pause and talk about other Earth surface processes that we worked on. This is rockfall in Yosemite National Park, where Jimmy Green, who's the OPTEC representative, was trying to sell an instrument to the Park Service. He scanned an area that happened to be the source for a major rockfall that closed down Curry Village for a while. We've scanned, we came back, rescanned, aligned it, and was able to difference it. So we are now virtually up in this rockfall, and we're actually going to go into this rockfall. We've been able to do volume calculations. They've never had a mechanism for being able to do reliable volume calculations. And so we're effectively climbing up there. I don't care for heights, but I could go into the cave and spend a lot of time really working in this in a very safe environment. So we're now actually in that slab that was several meters thick. So with Earth surface processes, there's a lot of applications. I think there's an endless length of applications for it. I've got the rockfall, stream bank erosion, debris flows, which we're going to spend a lot of time on. My opening animation was for the Laguna Beach landslide. Now we're going to go ahead and take a look at a video. So this is where we're going to need sound, and I need to find my mouse. Here we go.
This is horrible.
So this is a debris flow on Christmas Day 2003 after the first major Southern California debris firestorm. And this is a guy, imagine coming out of your house and seeing flowing concrete going down the road. This is exactly what it is. There are boulders in here that are the size of wheelbarrows in small cars that are going down. And it's because this is effectively the consistency of a thin concrete. So you've got that whole mass. Look up here, you've got the whole boulder field coming down. There's part of some structure just being carried right down. This is debris flows. This is the power. And as an environment, as a culture, we're now moving up higher into the mountains, into the area where we're going to have more and more debris flows and more hazards with it. So understanding how debris flows initiate, and the whole process is kind of key to some of the stuff that we're working on. So, with this, so we hit the sound. So what did it look like upstream of this? This is the area that was burned. This huge chasm, over 3 meters deep and as wide, actually used to be a small little valley. You could see rills coming down through here, incising. You could follow it all the way up here, all the way up here. It was just a high-intensity rainfall event that completely inundated the area. These were some of the homes of people nearby, some of the less fortunate neighbors. This is looking up. This is a new sign afterwards. So the recipe, or the equation is quite simple. You take no vegetation, you take steep terrain, you take a bit of rain, you get rapid erosion. The USGS and NOAA are collaborating together on trying to develop debris flow warning system. What NOAA does is they count the raindrops that come in into the system, and we work on trying to understand what the debris flow hazards are with it. And so this is rainfall duration in hours on the bottom, and this is peak storm. So any rainstorm, or any storm that comes in that either has heavy rain or long duration, lighter volumes of rain can trigger a debris flow. So what we're worried about is anything above here. If you've got a storm that's coming in that's anticipated to be lower than this is where we place it down here. But these are site-specific. It's also terrain-specific as well as geology-specific. So we've got to really nail the geology part. And we've got to nail all this to be able to fold into the hazards. So this is what NOAA does is they take their tornado storm tracing trucks used for the summer and park them in Southern California during the winter. They count all the raindrops, and then we go ahead and then work on modeling it. This is the station fire, which we're going to spend a bit of time looking at. This is an outline, and you can see it had a very high intensity rainstorm event. The Earth surface process with the USGS, Kevin Schmidt, John Stock, and Mariana Henshaw have done numerous years developing techniques. These are overland flow sensors. We've got soil moisture probes. Their objective is to, as soon as the water hits the ground, to be able to measure how fast does it soak down in, and at what point do we have overland surface flow that contributes to debris flows. My contribution is to go ahead and produce high-resolution digital elevation models for them to do mapping, and I'm able to produce centimeter, 2 centimeter, 5 centimeter maps depending on the area, and then to be able to do the volume calculations on how things are going. This sphere on the right is something that we developed to go ahead and specifically do long-distance scanning. And some of the products that we're able to produce are high-resolution geologic maps of the areas where you have dry gravel, you've got rilling, you've got other things. So the ground-based LiDAR provides the map for the base for this. It also, we're able to go back and then do remapping of where we've got ridge scour, rilling, and so forth. So I'm going to start speeding up here because I've got a few more slides. We did start late. So in this spot here, we've spent 5 years trying to image an individual storm. On this one here, we finished our installation on November 12th. It was not supposed to have any storms or anything. That night, a rogue thunderstorm came through and produced a rainstorm event at 28 millimeters an hour. So this is what it looked like when we left the site. And here's what it looked like when we got out there the next day when the roads finally cleared. This is up on the ridge. You could also see the sensors coming down here, down through here. So we got lucky. We actually captured a rainstorm event. So overnight change, we have upwards of close to 2 meters worth of channelization down at the bottom. What we found was that over 70% of the material that came out of the storm came from the channels and not from the sides. And we were able to calculate the exact volume. What this works out to is somebody took a shovel and went out there and removed 2.6 centimeters worth of material across the whole area. That volume is what went down into the neighborhoods below. We also found some other processes. We got some debris spouts. As the material came down, we had coarse gravel here. The water dropped out and all the sediment ended up leaving. Here, we've got one last 3D animation. And so go ahead and put on the glasses. And what we're going to do is we're going to fly in. The white data are from the day before the storm. The yellow are the day after. And then the blue are at the end of the season. We're going to go up this channel. and take a very close look at the deformation or the sediment flux through the basin. And this is one where I need the glasses on. So here's the blue. You're able to see the bottommost channel. Here's yellow, and then the white. You're going to see throughout this data set, there are, again, the white's the base, the yellow, you're going to have channel comes in, and then it gets filled in with the next storm, and erosion takes place elsewhere. So you have this living organism where sediment's being moved, it's being stored in one spot, just to be cleared out with the next storm. See the channels coming down through here. Now we're going to head over to where we saw those debris snouts in a second. And again, what we found is most of the material came from the channels. So what's with these channels? With the vegetation that's been gone or stripped away, there's nothing to hold the soil back in. Wind, other processes are allowed to come in and then completely move the material down into the channel. Then when you get enough rain, then you flush this out. And at some point, you flushed out most of the readily available material, and you end up with having a system that is back to a relatively safe. So here's a spot where you see a blue channel through here. So the first two times, nothing took place. Then we had, this is 1.25 meters worth of erosion here. So we head over here, we have white. Now we have blue and yellow on top. So this is deposition. This is where we're having the debris snouts that were being formed. We're going to see a yellow channel coming up, where then blue filled it in. So again, it's this living organism where we've got the material that are coming down and then back up and down. And so this is the sediment supply as we're trying to move it out of the system. Got one channel here, another channel here. We're going to drop down and then back out. And you can see the various timelines through here. I'm going to do a couple pictures of what dry gravel looks like, and then I'll wrap up. So take the glasses off. Here's dry gravel. This is just material that's come down in. This is what gets mobilized. This is the concrete that we saw in the video. This is basically loading the gun, pulling the trigger back, just waiting for the rainstorm to come in. When we're walking along here, one step here would create like a little landslide-like feature that would just go on. Some of these would move a fair amount of material with each step that we took. I don't think I can emphasize enough. I think we're in a very exciting time in geodesy right now. There's a lot of things that are going on. We've got advances. It's at the point where now I think we should turn that telescope in and start looking inward, looking deeper at some of the processes, the fine-scaled features that make up the larger scale picture. And test a number of different things. Another thing I do is a fair amount of development. So as we start looking in closer, if I were to give this talk in another 5 years, this is going to seem old school. The laser scanner that I initially bought, it was a really fast one, 2,000 points per second. There are now ones that you could probably see downstairs that are going over 1,000 points per, 100,000 points per second. There's a new 1 micron system that will image snow and ice out at 4 kilometers. Our big limitation right now is the computing power. I can't tell you how many times my computer crashed in preparing for this talk. Countless crashes, because if you've got 100 million data points, I've got projects that have 500 million data points. I've got some of the fastest regular computers that I could buy. It takes weeks to process some of the data with all the data points. So I'm hoping in the next 5 years we're going to see some incredible advances. And I'll end with basically a quote from William Bowie, which the lecture was named after. Before one could study the efficiency of the great geophysical facts and comprehend them, he must know the shape and size of the Earth with considerable accuracy. We've come a long way since Bowie initiated AGU, and our accuracy is increasing. We're looking at larger areas. Our questions keep on expanding, and it's an exciting time. Thank you.